am going to get a 1 in one of those rolls. Okay, I love that, thank you. Same thing with 2, 3, 4, 5, and 6, right? Good. Good. So, oh, I like that word too. That was good, that was good. But you can't see that yet, hang on. Austin, could you point that, the AV, hit that button and point it there and hit AV mute? That should turn the screen on. Maybe middle right side. Thanks, sir. All right, Lauren, here we go. This is my Microsoft Excel die roller. It's the same thing as your dice, except not quite as much fun because you don't do anything except I push the F9 button. Your next project has a lot of this involved with it. So if you look at that pips on current roll spot up there, I'm going to click in that space. See this command right here? It's called rand between 1, 6. That is the die roller command in Excel. It randomly generates a number between 1 and 6, and then reports that number back. It's the same thing you guys did with randint on that one quiz. It's the Excel version of that. So now every time I press the F9 button, I'm going to get another die roll. There's another one. There's another one, there's another one, there's another one, there's 6 rolls. Lauren! What the hell? She's lying to me.
I said supposedly.
You said supposedly. You did cover yourself pretty well by saying that, didn't you? So, because right now it looks like the probability of rolling a 2 is 1/2.
Yeah.
Half the time you're going to get a 2.
You have to increase your, this was like she was saying, you have to do it more times.
So I bring back my point to what does it mean to have a probability of 1/6?
On average, over the course of enough rolls to get that 95% or whatever have you, then you will get at least the same amount of 1s as 6s as 3s.
That perfectly said. You have, it's not a promise over a set number of trials. It's a guarantee over an infinite number of trials. You will get 1, 6, 1s in time. What is in time? Technically it's off to infinity.
Which means you're never going to get it.
Good. Lauren, here. I need my statement. I'm going to hold down the F9 button. You watch that pie chart, friends.
Oh my gosh.
That's weird, isn't it?
It gets pretty close. Like that's
What is pretty? Hang on a second, make this work.
It evens out.
It starts to even, yeah.
Uh-huh. So how close is close? Are we close yet? Are you close enough yet to be happy with those being 1/6? This guy's still catching up, isn't he? Remember how? Did you notice? Did you notice the orange one was the last to join the party?
Yeah.
He was opening up very slowly, and then all of a sudden, what happened? He caught up. Now, think of this as when people go to Vegas, and you're watching a little old lady play the one-armed bandit, and she's playing the machine, and it's not paying out. You start getting excited. You start going, that machine's due, that machine's due, that machine's due. So as soon as the little lady gets up, they go bum rush that seat and try to grab that machine. In theory, that makes sense if you had infinite time. The problem is, you never know when it's going to happen. So waiting for that to happen is no more or less logical than just picking any random machine because it's all one out of the number of outcomes. Does that make sense? Just like that, that's pretty damn good. That orange one leveled off, seemingly all at once. As a matter of fact, FYI, just so you know, the chance of me going pop, 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 pop 6 times and getting 1 of each is 1 in 120. It happened. You got it. Jacob got it. It happened to me once in 20 years of doing this class. And the class was like, I don't believe you anymore. They didn't believe the bit about it should clump like it did. Because it happened perfectly. And I said, well, watch it again. And I started it up again and hit it 6 times and it didn't work. Like, but we saw it. We just saw it. So it can happen. It's not 1 in 120 because we just saw it. I'm like, shit. I hate it when the probability catches up to me. But most of the time, there's a 119 out of 120 chance that it won't happen. Because there's only 1 in 120 that it will happen. So, but Jacob just saw it. Awesome. Now do it again, and do it again, and do it again, and do it again. And you'll see the average kick in. Beautiful. Thank you, sir. So now, take a look at where we are right now. We've gone up 3,700 trials. That looks like 6 equal pieces, right? Yeah. But it's not. 660, 630, 680, 630, 680, 690.
You're never going to get there. That's the thing. It's because
you're never going to get there.
The infinite number on the bottom, which means you're never going to get there.
Do you see how this is related to the last question on your project?
Well, the exponents never hit.
You're never going to get to 0, but you can get as close as you want.
Yeah.
You can get as close as you want. If you want to be within a half, look at the fractions. These are the percentages that we're getting. Remember what we said we should be getting? 16.66%? Look what's coming up. Now, those are not perfect. Let me show you. Hang on. Let's do this for a sec. Let's increase the decimal on this bad boy. Where's that button? Is it this?
Yeah.
Let's decrease. There's the decimals. Let's let it keep going again. It's not going to be perfect. But eventually, the ones have already stabilized. If I let this thing go long enough, the 6s are going to stabilize. Let it go long enough, which will take 100 times longer, the next row of 6s will stabilize. I'm going to let this keep playing out. I'm going to let this keep going. And we're going to come back to it after it's up to about 100, there are like 50 or 60,000 trials.
So I think I was misled. On the project I did 0.4 to the power.
Oh, you did. You were not misled. I'm saying the same kind of mathematical point is happening here as is happening there. These will never get to exactly 1/6,
Oh, okay.
but they'll get as close as we want them to get to 1/6, depending on how many trials we let them run.
I got 100%.
No, you didn't. You got rounded to 100%.
Okay.
It never can equal 100%.
Okay.
It can round to 100%. Yeah, I know your TI eventually will say 1.
Yeah.
That's because your TI is misleading you. Right? Because that's like saying that 1 minus 0.4 to the x power can... Think about it this way. Exponentially, thank you, if you don't mind. The graph you're looking at is an exponential graph. This is the graph of 0.4 to the n power, or the x power. This thing is going to forever head out this way.
Yeah.
But it can't hit 0, because if it could hit 0, that's like saying, if you keep taking fractional values of a non-zero number, you can't actually equal 0. It breaks the rules of multiplication by 0. The only way something times something else can equal 0, the only way that can happen is if one of them, if not both of them, are 0. So that would mean that at some point, to get this to equal 0, one of those 0.4s would have to be 0. That doesn't make any sense. It's not 0.4. Does that make sense? Now, you didn't have to explain it that way on the project. That's just one way of explaining it, a very quick way of explaining it. You can explain it any way you want to. So the damn TI can mislead. And that's the problem becoming slaves to technology is sometimes it gives us results and we're like, well, it says 0. It might be 0 enough, but it's not actually mathematically 0. Fair enough?
Yeah.
Ish, we'll come back to that too. So if you weren't misled by this, it's the same exact idea actually. What I would like to do though is, are we in agreement that if we let that little guy keep going, it's going to hit the 1/6 as close to 1/6 as we need to go? I think that's a fair assessment. Now, what I'd like to do is I'd like to add to this distribution here. So I want to keep this. I like this column right here, because he's doing a pretty good job of talking about what could possibly happen in the experiment.